So why is it that we went through and discussed what happens with all these forces, or what could happen with all these forces at higher and higher temperature? Well, remember a couple of things that we've talked about previously. We know that the universe is currently expanding. And if the universe is currently expanding, and you go back in time, then everything had to be closer together. Well, what happens to the temperature of things as they compress? They naturally heat up. So if we go far enough back, then we have to take everything that is the universe and squeeze it down into a teeny tiny little thing. Whatever that thing is, it's going to be incredibly, incredibly hot, which means to be able to understand what was going on, we have to know what's happening at these very, very high temperatures. So, because we have this theoretical idea that we can unify forces at higher and higher temperatures, that's going to help us understand what's happening at the very early universe. So at the very beginning, we have the moment we refer to as the Big Bang. Now, this may be one of the worst named things in all of astronomy. The Big Bang was neither big, nor was it loud. It wasn't loud because nothing existed yet, so you couldn't exactly have sound, and we believed that the universe was super, super tiny at that stage. So it was not big or loud, but this is the name that it got stuck with. For the first 10 to the negative 43 seconds, the universe was so hot, it was over 10 to the 32 Kelvin, that to be able to describe what was happening in the universe at that time, we have to have a theory of everything. Now, we do not have a theory of everything. We have some approaches, but all of these approaches don't actually agree with each other on how things should behave. So although we've got different people working on it in very different ways, we don't actually have any single idea. What this means is for this first 10 to the negative 43 seconds, we do not know what was going on in the universe because we do not have a theory of everything. This very first short time is known as the Planck era, and that's the first 10 to the negative 43 seconds. Now, one thing we can say is that the universe expanded, and as it expanded, it cooled. So at 10 to the negative 43 seconds, the universe cooled off enough that gravity froze out. What we mean by freeze out is that it cooled off enough that gravity became its own force. It started behaving distinct and differently from the other forces. Now, the other forces, the strong nuclear force, the electromagnetic, and the weak nuclear force, were still all unified, which means we have to have a grand unified theory to be able to describe what was happening during this time. We have to have the grand unified force and gravity. Now, we have many different approaches to a grand unified theory. They don't all agree on everything. However, there are certain themes that they do all agree on. What that means is we have a very slight, vague idea of what the universe could be like during this time. Once we finally get a single grand unified theory, then we'll have a much better idea. Now, one thing we can definitely say is the universe continued to expand and therefore continued to cool. So that at 10 to the negative 35 seconds and 10 to the 27 Kelvin, the universe cooled off enough that the strong nuclear force froze out. Again, that means that it became its own distinct force. Now, when the strong nuclear force froze out, it began what we refer to as the inflationary epoch. So what we believe happened is that the entire universe actually went through an energy level change. If you remember back when we talked about atoms, we talked about the electrons can only be at certain positions in the atom, meaning they can only hold certain amounts of energy. And for the electron to fall from one level to another, it has to release that energy, which means it gives off light. Well, the entire universe was kind of like it was at a higher energy level. And because it was a higher energy level, that once the strong force froze out, it allowed it to transition to a lower energy level, but that energy had to go somewhere. And for a very brief amount of time, it actually went into the expansion of space, so that space expanded at a much faster rate for a very brief amount of time. Again, this is the inflationary epoch, and we'll discuss it more later on, because it helps us understand and overcome some of the problems with the Big Bang. Once we have gravity and the strong force acting distinctly, we then enter into the electro-weak era. During this time, we have the strong force, gravity, and the electro-weak force, the unification of the electromagnetic and the weak nuclear force. Now, at this stage, we are actually in the realm where we can do experiments to see what was going on. We have verified the electroweak force in labs. So we're starting to get a good idea of what's happening here. It's still absolutely not perfect, but it's at least in a realm that we have the technology to be able to do experiments to see what was going on. Now again, the universe continued to expand and cool, and at 10 to the negative 12 seconds and 10 to the 15 Kelvin, the universe cooled off enough that the weak force and the electromagnetic force finally froze out, so that we now have all four forces behaving distinctly. Now, something I want to point out real quick, you don't have to know the exact length of each of these different eras. Do know kind of the general properties of the eras, and that we're getting to slightly longer and longer times as we go through each, but you don't have to know the exact number for exactly how long they were. Here is our second lecture quiz question. E equals mc squared shows mass can be turned into energy, and energy can be turned into mass. A, true, B, false. Go ahead and think about it, and we'll discuss in just a bit. Alright, do you remember what E equals mc squared means? The E is energy, m is mass, c is the speed of light. So it's showing that energy and mass are related. And you can convert mass into energy, which we've talked about before. That's what happens in stars. As stars fuse, they convert a little bit of mass into a whole lot of energy. But you can also go the other direction. If you get lots and lots of energy together, you can actually create mass. With this idea, it is possible to convert energy into mass. This happens in the process we refer to as pair production. The idea is that we have two high-energy gamma-ray photons. Remember, photons are particles of light. If these two things crash into each other, it is possible that we have so much energy concentrated that it creates mass. Specifically, it creates two particles. It creates a matter particle and its antimatter equivalent. We talked very briefly about antimatter previously, but as a quick review, for every particle there's an antimatter equivalent. And the antimatter equivalent has the same amount of mass as its particle equivalent, but it has opposite charge and opposite other fundamental quantum properties that we're not getting into. Okay, so for a great example of this is the electron. The electron is negatively charged. The antimatter equivalent of the electron is going to be positively charged but have the same amount of mass. This is the particle we call the positron. So in pair production, we always create two particles, the particle and its antiparticle equivalent. Now when matter and antimatter come together, they annihilate. What this means is the particle and its antimatter equivalent come together, and that then produces light. They go back into being gamma-ray photons. Now at the beginning of the particle era, this right after the electroweak era, at the beginning of the particle era, this whole thing is in balance. For every pair of particles that's being produced, a pair of particles is being annihilated. However, as we move through this era, the universe continues to expand and cool. As this happens, that means there's going to be less and less energy available to form particles. So at the beginning of the era, we can create all the particles, high mass, medium mass, low mass. We can make them all. But as the universe expands and cools, we no longer have enough energy to create the high mass particles. We can still make the medium and low mass, but no high mass. Then as the universe continues to expand and cool, we can't make the medium mass particles anymore. We can only make low mass. And then finally, at some point, we're not even able to make the low mass particles anymore. We mentioned already that during pair production, we always create the particle and its antimatter equivalent. And when they come together, they annihilate. This actually leads to a little bit of a problem. The universe is over 13 billion years old, which means that all particles and antiparticles should have found each other by now, and therefore everything should have annihilated. Everything should have gone straight back into energy. And yet, we know that there's still stuff in the universe. Specifically, we know that there is matter in the universe. Well, what we believe has happened is that for every 1 billion antiparticles that are created, 1,000,000,001 particles are created. And we live in that extra 1 billionth part that was left over after everything else annihilated. Now, we don't know exactly why this happened. This is one of those ongoing questions that we're trying to research. Although we do have some possibilities and some things that we've seen in experiments that are giving us hope that we might be able to explain this at some point in the future. Now, again, something we know is the universe continued to expand and cool. As this happened, it got to the point where the entire universe was the right temperature and density to begin nuclear fusion. Now pay attention to what I just said. It cooled off enough for nuclear fusion. As we've gone through the whole course, have we ever treated fusion as a cold process? Absolutely not. This is what's happening in the center of stars. Okay, this is incredibly high energy. But it was so hot, it was so high energy in the universe before this time that fusion could not happen. I hope that that kind of gives you a feel for the incredible temperatures we're dealing with. Well, during this period where the entire universe was going through fusion, this is known as the era of nucleosynthesis. Nucleosynthesis means making the nucleus. Now, this period begins about 2 seconds after the Big Bang and extends for about 10 minutes after the Big Bang. And because we have fusion, this is then going to release neutrinos. Now, neutrinos do not interact strongly with matter at all. What that means is there should still be neutrinos out there that were formed during this period from 2 seconds to 10 minutes after the Big Bang. If we could figure out a clever way of detecting them, that would allow us to get a glimpse of what the universe was like 10 minutes after the Big Bang. Unfortunately, we're not there yet. We have had some experiments that show that these do exist. We have detected their influence on things, although we haven't found them. But hopefully we can soon, and that would be amazing.